So in our last example, we found the force on the bottom of the tank using these two concepts, the differential pressure times differential area, and that the pressure varies according to the differential equation dP dz is equal to minus rho g. Now what we're going to do is find the force on the side of the tank. And so we're going to follow a similar approach. Once again, we can say that the differential force is equal to the pressure times a differential area. Only this time our differential area is on the side of the tank. And so just for clarity, I'm going to call this dA2 and put a little subscript 2 there. And again, we can add normal vectors to this to get the vector form. And so normal vector points normal to dA2. So I can call this n hat 2. And you can see here that n hat 2 points in the minus y direction. And so n hat 2 is actually just minus j hat, where j hat is the unit vector in the y direction. So I can come in, drop little vectors here, get the vector version of this. And as we know, we're going to have to integrate both sides of this equation. This time, our differential area, since it's on this side, is in the x and z direction. And so dA is actually dx dz. And then, since we want it in vector form, we've got to add the j hat with a minus sign since it's pointing in the negative direction. All right, so let's go ahead and do our integral here. On the left-hand side, we just get the force vector. On the right-hand side, we're going to be doing two integrals. And we're going to have p, and we can sub in our dA here, dx dz minus j hat. And let's take a minute and look at the limits here. In the x direction, we're going to integrate along this line here, this direction here, and so that's 0 to d. In the y direction, or excuse me, in the z direction, the vertical direction, we're going to go from the top of the tank to the bottom. Well, we defined our coordinate system so that the top corner of the tank here is 0. And so what that means is that if we start at 0 and integrate to the bottom of the tank, our finished limit is actually a negative h. Okay, but now we need the pressure. Well, we can get the pressure, once again, using formalized version of fluid statics, which says dP dz is equal to minus rho g. And if we separate and integrate, we get dP is equal to minus rho g dz, or P2 minus P1 is equal to minus rho g times Z2 minus Z1. Now, you can imagine if we're interested in forces, there's actually a force on both sides of the tank that are equal and opposite caused by the force of atmospheric pressure. And so those cancel and we don't need them. In other words, we can work this from the gauge pressure perspective, assuming that P1 is 0 gauge, and we can call Z1 0 by definition. And so that lets us say that P as a function of Z is equal to a minus rho gz, minus rho gz. All right, so let's sub that in. Force is equal to the integral from 0 to negative h, integral from 0 to d of minus rho g z dx dz and a minus j hat. So we're getting lots of negative signs here. This might start to get a little confusing. Thankfully, these just cancel each other. Bing, 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 they're gone. All right, so the inner integral, the x direction integral, 0 to d here, there's nothing that's a function of x, and so we can write that as the integral from 0 to minus h of rho g z. The integral of dx is x, evaluate from 0 to d, just gives us a d. And then that's times dz times j hat. And so now we have this integral with respect to z. Well, z is in there, and so you're going to get rho g d. The j hat comes forward. And we're left with the integral here, which is going to give us a a z squared over 2. Z squared over 2, which we now need to evaluate from 0 to minus h, which finally gives us the value rho g d h squared over 2, and that's acting in the j direction. So the thing that's nice about this is that you can still just follow the math, but we found an interesting result here, didn't we? We found that the pressure acting on this wall creates this force that goes like h squared instead of just h.